So from last video, we saw this map. If I give you an LQ function and I define a map, which is called a phi g, okay, so let me remind you this phi g, if I evaluate on an LP function, it's basically the integral of the product of f and g respect to this d mu. And we saw from last time this phi g is in the dual space of LP. So now I can define a map that just takes any LQ function and I map it to phi g. We know this is going to be a well-defined map. And in this video, we're going to prove the main theorem that's basically saying this map is not only well-defined, but it's actually isometric and isomorphism. Okay, so here, isometric basically means, well, I have two normed vector space, so they have their both a metric space, they have their norm. So the norm will be preserved. So on the left-hand side, I have the LQ space, so the norm is given by the Q norm. And on the right-hand side, the LP dual space, the norm is given by the operator norm. Okay, so these two are the same. This is already proved in the last video. Okay, so this part isometric is automatically done. And isomorphism basically means it's an isomorphism as a vector space. Okay, you have a linear structure on either side. Okay, so this phi needs to be basically a linear map, and it's going to be injective and surjective. Okay, so that's basically what isomorphism of vector space means. Okay, so let me just say as vector space. Okay, so one thing is fairly clear is the following. So let's prove this. So first of all, this phi is clearly linear. So why is that? Well, this is just follows from the linearity of the integral. So suppose I have a times g1 plus b times g2, and I do the phi map. Okay, so if you think about what it does to a function f, that's just the integral of f multiplied by your function ag1 plus bg2 d mu. And because integral, everything is linear, so you pull out the constant and you do the summation of these two functions. So you have fg1 d mu plus b times the integral of fg2 d mu. And by definition, this is just a times phi of g1 evaluate at this function f, and also we have a b times phi of g2 evaluate at this function f. Okay, so if you forget about the f, then this is essentially saying this phi map. If I give you ag1 plus bg2, okay, as two functions and map to a linear functional in the dual space, well, that's essentially the same as a times phi of g1 plus b times phi of g2. Okay, so phi is going to be linear. Okay, so this is also done. Why is going to be injective? Well, there's one thing, if you remember, all the isometric map, they're all going to be injective. Okay, so isometric will imply injective. Well, the reason is that if I have some, say g is non-equal to 0, then if it's non-zero, then I know the Q norm of G is not equal to 0. And isometric map will preserve the norm. Okay, so the operator norm of phi G, the image of this G, is also not going to be equal to 0. And because it's a norm, so the phi G is not the zero map. Okay, so that's basically a map anything non-zero to non-zero, so it's injective. Okay, so that's pretty easy. So it really just comes to the last one, the surjective. Okay, so I basically need to show that everything in the dual space of the LP space comes from one of these phi of G. Okay, so I need to take any functional in the dual space of LP, and I want to show that this is actually given by some phi of G. Okay, I need to construct a G essentially. All right, so that's basically what we need to prove. So in this video, let's make a easier assumption. Let's assume that this mu is finite. Okay, suppose I have some finite space. And when mu is finite, one thing is fairly simple, is all the characteristic functions are in the LQ or LP there, anywhere, okay? So I can define the following. So let's define mu of E. So right now mu is just a map, evaluate on some measurable set E. I define it to be the phi of this chi of E, okay? So here, basically, chi of E is a characteristic function, so it's very easy to check because mu is finite. It's in the LP space. Okay, it's in the LP of mu. So phi being, well, I should say for every phi inside the LP space, the dual space of LP. Okay, the dual space of LP. So phi essentially takes an LP function and returns a real value. Okay, so now I feed in this chi of e is an LP function. It will return a value. Let's call it just mu of e. Okay. So I want to claim the following. So I want to claim that mu is a signed measure. So mu is a signed measure. Okay, so that's what I'm going to prove. Well, first of all, if I consider signed measure, basically two requirements, the nu of the empty set has to be equal to 0. So nu of empty, basically by definition, is the phi of the characteristic function of the empty. While characteristic function of the empty set is just the 0 function. Well, phi being a linear map, it maps the 0 function to 0, so there's really nothing to prove here. And second, I need to show that if I have a bunch of disjoint sets, then mu is sigma additive. Okay, so let's let these En, they are disjoint. And then let's consider E, which is equals to the union and go from 1 to infinity of these En. Okay, so essentially I want to prove that the nu of this E is the sum of nu of En. So I need to compare the characteristic function of this E versus the sum of the characteristic function of this En. So moreover, I need to compare them in the LP space. I need to treat them as LP functions. So let's consider chi of E minus the chi of En. Well, I do the partial sum and go from 1 to k. Okay. Let's consider their p norm, maybe just raised to the power p. Well, by definition, this is just the integral of the absolute value raised to the power p d mu, and let's write the absolute value as the summation of the tail. Okay, so chi of e is the basically the sum, the infinite sum of these chi of En. So the difference is you sum when n going from k plus 1 to infinity of these chi of En. And good thing about these chi of En is that they're disjoint. So when you take their sum, they're basically either 1 or 0. So it doesn't matter how many power you raise to the power p, is still 1 or 0. So that's still the characteristic function. So this is still the integral of the summation chi of En. Okay, and going from k plus 1 to infinity d mu. So by definition, this is essentially just the sum of all the k going from k plus 1 to n going from k plus 1 to infinity of the measure of this En. Okay, and because if you consider what happens to mu of E, so mu of E, because mu itself is a measure, so this is the sum of the mu of En, n going from 1 to infinity. This one converges. Okay, this is less than infinity. We're assuming we're in a finite measurable space. Okay, so the summation of this tail needs to go to 0 as k goes to infinity. Okay, because the summation of mu of En, they converge. You're now only summing up the tail, so that goes to 0. So moreover, this essentially just shows you that the summation of these chi of En, as in going from 1 to k, that's going to converge to chi of E, not just pointwisely, but also in the LP norm, okay, in LP norm. Okay, so because their P norm goes to 0. All right, because they converge in the LP norm and your phi is inside the LP dual space, so this is LP dual. So remember the dual space essentially consists of all the continuous linear maps. Okay, this phi is continuous. So now you have something that converges in the LP norm. So when you apply to something continuous, it still converge. Okay, so basically that tells you when you apply these sequence, these partial sum and go from 1 to k of chi of En, okay, that's going to converge to phi of chi of E. Okay, that's convergence inside the real basically. And because this phi is linear, so now on the left-hand side is a finite sum of these chi of En. So you can break it into the finite sum of phi of chi. So this is n going from 1 to k of phi of chi En. Okay, so, and by definition, each one of them is just equals to the new map, okay, the new of En, here, n going from 1 to k. And this partial sum is converging to the right-hand side, which by definition, just mu of E, okay? So nu of E is equals to this infinite sum, okay? So we have this nu is a signed measure. And now we have a signed measure nu, so nu is a signed measure. And we want to show that this nu is some kind of integral, basically, okay? So we want to show that this phi, if I evaluate on some function f, is the integral of this f with some another function g. So essentially, I need to show this nu is some kind of a Radon-Nikodym derivative respect to mu, okay? So that's essentially what we need to prove if you think about it. Okay, so now let's think about if I want to have a Radon-Nikodym derivative, I better have some absolute continuity. Okay, so let's assume I have mu of E is equal to 0. Okay, so if mu of E equals to 0, then the nu of E, by definition, is the phi of the chi E. Okay, but chi E, because mu of E is going to equal to 0, this chi E is going to be 0 almost everywhere mu. And in the LP space, if you only differ on a null set, they're basically the same function, okay? You quotient out all these kernel. So this is essentially the same as phi of the 0 function because they're just the same in the LP space. And well, we saw this is equal to 0, so we have mu of E is also equal to 0, okay? So basically that proves I have mu is absolutely continuous respect to mu. So by definition of the Radon-Nikodym derivative, recall we have here, we assume there are finite measures. That's why we need the sigma finite assumption anyways. All right, so by the Radon-Nikodym derivative, I can find a function g. So here, I don't know where this g lives, but I can write nu of E is equals to the integral of this g of d mu. And if you recall, let's assume any function, simple function f, which is equal to some ai chi of ei. Well, then basically, if you want to consider what happens to this phi of f, okay. So by definition, this is just equals to summation of ai nu of ei, okay. Well, this each nu of ei is now an integral of this function g, so this is integral of ai, well, ai integral over ei, but you can also say, I missed the e here, so this is integral over ei of this g d mu. Well, but another way of writing integral over this ei is you say, well, this is just ai times g times chi of ei d mu. And you can say this is the integral of the summation of ai chi of ei times g d mu, or you can say this is just the integral f g d mu, okay? So for every simple function f, the phi of f is in this desired form, okay? It looks like phi g of f, okay? Well, we still need to check a few things. So first of all, I need to check this can be extended to any measurable function f in the LP space. And second, I actually haven't shown this G is inside LQ, so I have two things left to check. So one, I need the following. So I need, first of all, this phi is indeed equals to this phi of G. And second, I need to prove that this G function is inside the LQ space. Okay, so once I prove these two, then I show that any functional phi is in the form of some phi of G. I will leave the proof of these two technical details to the next video.